like to share that more than 200 researchers from various universities in Chile and abroad have registered to participate in today's webinar. On behalf of the organization committee, I take the pleasure to thank for their participation in this seminar. In this webinar, we have eminent people to share their scientific knowledge about latest advances in research on the valorization of lignocellulosic biomass with us. Dr. Dorothée Laurenti from the Research Institute on Catalysis and Environmental of Lyon, France, and Professor Dmitry Murzin from Åbo Akademi University, Finland. The millennium nucleus of catalytic process towards sustainable chemistry is established to address the development of energy sources for the long-term usage, with free of pollution from the available sources. Decreasing our reserves lead to increase the price of it, with high demand in day-to-day life, as well as usage of it is the manifest rate of greenhouse gases. And these are the facts which motivate the research community to seek new resources to replace fossil fuels. Thus, biomass is the only source for the production of fuels and chemicals that can replace oil. In this way, the main goal of this nucleus is synthesis and design of new catalytic materials for the production of strategic chemical products from derivatives of biomass using various catalytic processes. This nucleus is financed by the Millennium Scientific Initiative of the Ministry of Economy and is made of about 13 academics and 50 researchers from the Pontificia Universidad Católica de Chile, Universidad de Concepción, Universidad Autónoma, y la Universidad Católica de la Santísima Concepción, with consolidated experience in the area of inorganic chemistry, physical chemistry, theoretical chemistry, and chemistry of lignocellulosic materials. In addition to 4 senior researchers of outstanding and recognized international careers from the Universidad de Concepción, Chile, el Instituto de Catalysis y Petroleoquímica, Spain, University of Oklahoma, United States, and University of Notre Dame, France. The center is hosted in the Pontificia Universidad Católica de Chile in Santiago de Chile. Now, Dr. Dorothée Laurenti from the Research Institute on Catalysis and Environmental of Lyon, France, will be presenting the latest advanced research techniques on the valorization of lignocellulosic biomass, intellectually entitled Lignocellulosic Biomass, Catalytic Conversion to Chemical for a Safer and Greener Future. Dr. Laurenti has completed her PhD in Marseille in 1999 and held postdoctoral position in York and Lyon University. She's working as a CNRS researcher in the field of heterogeneous catalysis. Her area of research interest is developing of a catalysis for hydrotreating reaction and for biomass conversion. She has published 56 research articles in international reputed journals and field 3 patents and participated in 60 conferences. Please, if you have any question in the presentation, please ask them by chat, for which we will provide about 5 or 10 minutes, and then to answer them in the end of the presentation. Please keep your microphone off during the presentation. Dr. Laurenti, thank you very much for your participation in our webinar. Please, can you start?
Thank you very much, Mr. Chairman. I hope that everybody is hearing me. I'm very pleased to be here today, and I would like to thank the organizers of this webinar because it's a pleasure to be with you today. And I have changed a bit the title of my presentation, but don't worry, it is exactly the same. I didn't change the topic, so I'm going to start. So all of you know that the Earth is not feeling very well, and this is because of the emissions of CO2 and other pollutants and increased temperature. There is a global warming, and as the petroleum is a non-renewable source of carbon, we need to limit the use of fossil resources. It is not exactly the end of fossil resources because there is no depletion of these resources. There are still a lot in the world, but the extraction becomes more and more difficult, and we have to intensify the processes to heavier fractions. Also, we've got a fluctuation of the prices and a political use of it, which is not very nice. And then we need to gain in sustainability and to reach a neutral carbon world, and to use renewable energy source as an alternative for chemicals and fuels. Just putting, sorry, okay. Then, lignocellulosic biomass is a well-chosen resource to do that, because it is abundant, it is non-competitive with food most of the time, and it is chemically interesting. Why chemically interesting? Because it is composed of three main components, which are cellulose, hemicellulose, and lignin. And these macromolecules can be the precursors for sugars, acids for cellulose and hemicellulose, and for aromatics and phenolics for lignin. But compared to fossil resources, the biomass feedstock, the lignocellulosic biomass feedstock, are more complex. They are highly functionalized and sometimes unstable. They contain oxygen, sulfur, nitrogen, but also other contaminants like chlorine, phosphorus, and metals, and a lot of components can be in those materials. And they sometimes require polar or aqueous conditions or very extreme conditions to be transformed. And you can see some example of lignocellulosic biomass, and you can imagine that there is a very large diversity, which is inducing a variation of the composition in the three components, cellulose, hemicellulose, and lignin, but also the other contaminants. It induces also problem of storage and pretreatment of the feedstock, and increase the infrastructure costs overall. And last but not the least, it is abundant, but it is still limited. And we are not going to cut every trees. We need to valorize the wastes from this biomass, and we need to identify the target to transform the biomass in purpose and properly. In traditional refinery, we produce, of course, gas and oil. In
we will wait for a second between the connection is reestablished. Please be patient, because you know we have some problems with the internet. But wait for a while. In the meantime, Professor Dorothée is reestablished her connection to the internet again. Please, the video take a lot of internet resources. Please, could you turn off your camera in order to increase the speed of the connection for the Professor Dorothée? Please have patience. We are working to reestablish the connection now. Please be patient. We are working. We have we are thinking in other solutions. Please keep in connection. Okay, I apologize for this inconvenience, the internet inconvenience. We will, Professor Dorothée, we will start the presentation in a while. And now we will start the presentation of the Professor Dmitry Murzin. Alejandro?
Hello? Can you hear me? Yes. We are honored to present the next speaker of this webinar, Professor Dmitry Murzin. Professor Murzin studied chemical engineering and chemistry at Mendeleev University in Russia. He obtained his PhD in 1989 with Professor Temkin at Karpov Institute of Physical Chemistry, and in 1999 was awarded a doctor science degree. After research visits to University of Strasbourg and Åbo Akademi University in 1995, he joined BASF, returning in 2000 to Åbo Akademi as a chair of chemical technology. His main interests are in heterogeneous catalysis, catalytic kinetics, and chemical technology. He has authored 6 books, 800 articles in peer-reviewed journals, 4 patents, 24 plenary and 29 keynote and invited lectures. His age index is 60. We thank very much Professor Murzin for participating in our webinar. The talk of Professor Murzin is entitled Base Catalyst for Biomass Valorization. Before start, we ask the public to maintain his micros off during the presentation. If you have any question, please write them on the Zoom chat. Even in Spanish, we will translate the question to Professor Murzin. So Professor Murzin, please, the floor is yours for your talk. Thank you.
Thank you very much. Can you see the screen?
Yeah, yes.
Yeah, so you see the screen. Because I have information, my screen sharing is paused, so I don't know. I think, but you still can see it.
Yeah,
oh, good.
No problem.
So thank you very much for the introduction. It's a great pleasure to give this talk. Certainly it would be better if I would be physically present in Chile, but that unfortunately is not possible. We all know what is the what are the unfortunate reasons for that. So my talk was supposed to be about catalysis by bases, and in that sense, it would be better if the first presentation would run a bit smoother than it was, because it would otherwise give a better introduction to what I am going to say. But in any case, we have what we have, so then I will continue. Why did I select catalysis by bases? What was the reason for selecting this topic? We all know different type of catalytic materials, that they are subdivided by metals, metal oxides, sulfides, acids, and bases. And up to rather recent years, the main focus of research in heterogeneous catalysis was in the first 4 blocks, what I have here on the slide. As for the catalysis by bases, I have listed here a few materials, calcium oxide, magnesia, potassium, and sodium oxides. If we look at the strength of base catalysts, those type of materials, they're somewhere in the middle of the scale. And then there are also hydrotalcides, which are even less basic, and sodium hydroxide together with sodium on alumina will be the strongest known superbases. So first I want to start with homogeneous base catalysis. Actually, it's not a curiosity. Self-aldol condensation of butanol is a 1,000,000 tons per year scale reaction, and what we see here on the slide is the aldol condensation of butanol given this type.
Excuse me, Professor Murzin. Excuse me. We are seeing only the first slide. I noticed that you are talking about other, but we are only seeing the first one. Can you take that, please?
You see only the first slide. Okay. So,
yes.
Okay. How can that be? Is this better now?
Yes.
And display settings for presenter, because I don't know what you see. That's my problem.
Yeah. No, now we are seeing the second one.
Oh, you see the second one. Yes. So
with
now
metals, oxides, sulfides.
yeah,
yes.
I think I can start all over again. Probably not with the intro, not with the acknowledgement to the organizers. That will be too much. But once again, so there are these type of catalytic groups which we all know, and then I will focus on bases. So the strength of base catalyst is different, and as I mentioned before, unfortunately, without you being able to see the screen, is that the catalysts differ in terms of the basicity. So why catalysis by bases, or why heterogeneous catalysis by bases? Before, I want to say a few words about the homogeneous catalysis by bases, and that's the slide which we didn't see. before you, and I was going to introduce the self-aldol condensation of butanol, which is once again a multi-million tons per year reaction or process. And this is some sort of downstream process of hydroformylation, which is one of the most important homogeneous catalytic reactions itself, where during hydroformylation, olefins react with the syngas, giving a mixture of linear and branched aldehydes, which are then condensed using sodium hydroxide. In fact, the reaction occurs in an aqueous organic mixture. From where, what do we do with the product? So once again, this what we have is the self-condensation of this aldehyde, butyraldehyde. Then finally, we have that compound, which is 2-ethyl-hexanol, and then it reacts with phthalic anhydride, giving this product, which is DOP, dioctyl phthalate, the compound which is used as a plasticizer for PVC. So that's what I wanted to say about homogeneous base catalysis. Heterogeneous catalysis by bases was not in the focus of research of our community for a very long time. I still remember the plenary lecture given by Professor Hattori, and that was in France, 93, so it was the previous century, in Poitiers, where Professor Hattori had to apologize because he was saying that I'm going to talk about heterogeneous basic catalysis, and that's probably of no interest for the majority of people sitting in the audience. The things have changed since that time. In his presentation, he was talking about calcium oxide, magnesia, and a few other oxides. Now let's look at the catalysis by bases in the connection of biorefineries. We all know this famous transesterification reaction, where triglycerides react with methanol, giving glycerol and a mixture of FAMEs, so fatty acid methyl esters. And this type of reactions can be catalyzed by basic solid catalysts, including calcium oxide, but also hydrotalcides. So a little bit of time I will spend about hydrotalcides. What are they? They are double layer hydroxides. They're formed in nature, having this general formula, what I have here on the screen, where we have two types of cations. One is typically Mg, but it can be also nickel, zinc, or copper. And then 3+ is typically aluminium. And then we have this part which contains then OH groups, and then what we have here is N ions. So these hydrotalcides, double layer hydroxides, they have both acid and basic sites, and then the nature, strength, and relative amount of sites would depend on the nature and the molar ratio of cations present in these materials. What is important is that hydrotalcides should be properly activated, so thermal treatment or calcination is important, and the basic character of the materials increases when we elevate temperature. In some of the cases, these non-thermally treated hydrotalcides are not catalytically active at all, and then we need to have a certain thermal treatment to get this catalytic activity. This type of materials became rather popular some years ago, and here I have a reference to the work done by my friends and colleagues from University of Oviedo from Spain, where they were studying aldol condensation of an aldehyde, not with another aldehyde, as an example I was discussing before, but with a ketone, with acetone. So then we have either this type of compound, which upon further hydrogenation can be used as a part of gasoline, or the continuous condensation then would result with this type of bulky compound. Further hydrogenation of that can lead to something which would resemble a diesel. The aldol condensation reaction mechanism starts with abstraction of a proton to produce the enolate. So therefore, we need to have a base here. Then the next step will be the condensation per se, giving an aldol ion, and then further transformations will result into an aldol or ketol. And then the next step will be, actually the final step, will be subtraction of water or dehydration of aldol or ketol, finally giving alpha beta unsaturated carbonyl compounds. And this step can be catalyzed either by acids or by bases. In connection of biomass transformation, it's actually interesting to consider a little bit more complicated reaction, which also comprises aldol condensation. In principle, we can start not only with aldehydes, but we can start with alcohols. So then the first step will be dehydrogenation on, for instance, metal sites, producing an aldehyde, then aldol condensation on basic sites. Then we have this dehydration reaction requiring either basic or acid sites, and then hydrogenation. So this complex reaction is called the so-called Gerber reaction, and it gives a possibility to produce long chain alcohols, starting from alcohols with a shorter chain. For instance, we can start with C2 alcohol, and then we can get butanol. Or we start with C4, then we get C8. So this Gerber reaction is not new. The products, what we are interested in, were somehow related to plasticizers and fuel compounds. And then the research, what we were doing, we were dealing with C4, C5, and C6 alcohols. I will start first with C4, C5. And this work was done together with my very good friend and collaborator, Irina Simakova from Novosibirsk. And then I will later on discuss this Gerber reaction using C6 alcohols. By the way, Gerber himself published the first paper on that topic, if I remember correctly, it was 1902 or something like that. And almost at the same time, or 1 year earlier, later probably later, there was a paper of Markovnikov, the famous author of the Markovnikov rule, also on the same topic. So in the Russian literature, this reaction is called Gerber-Markovnikov reaction. First, I want to say a few words about the formation of C5 alcohols from biomass. From where do we get them? Probably Dorothée would discuss, or was planning to discuss something like that, but I have to do it now. When we start with glucose, by dehydration, we get first HMF, then further hydrolysis will give us levulinic acid together with formic acid. Further hydrogenation and dehydration would result in gamma valera lactone, and then upon subsequent hydrogenation, we can get valeric acid, and then further hydrogenation will give pentanol. So that's the route of producing pentanol from biomass. The strategy of applying this heterogeneous base catalyst, in fact, can be different. And I will say few words about different type of strategies. In principle, what we can have a metal on a support and use a homogeneous base, for example, sodium hydroxide. We can have a metal support or metal on a support and then a heterogeneous base. It's also possible to have a metal on a base support, and the metal we need because of hydrogenation and dehydrogenation step, which I mentioned before. And then in principle, it's also possible to have a metal on an amphoteric support. Few words about the experimental part, just for you to have an idea about how experiments were done. So this is the reactant. It was put in an autoclave in addition to the solid sodium hydroxide. Experiments were done in this range of temperatures, either under hydrogen or in inert atmosphere under nitrogen. A different type of catalysts were tested, different metals, noble metals, iridium, rhodium, ruthenium, palladium, platinum, on different type of supports with different nature, more acidic, less acidic, amphoteric, almost inert like silica. And then here there are the methods for catalyst characterization and the methods for characterization of reaction products. The catalysts were prepared in Novosibirsk, and they had very high dispersion. As you can see from the size of metal clusters, they were in the range of approximately a little bit higher nanometers. So a different type of alkali agents were tried, sodium hydroxide, potassium hydroxide, then MgO, aluminium, hydroxide, sodium, and calcium carbonates. It turned out that only 2 alkali agents were efficient, sodium hydroxide, and then the majority of experiments were done using this type of catalytic system. So metal on a support, and then dry sodium hydroxide, which was introduced into the reaction mixture. First of all, there was no reaction without a base, whatever it was, hydrogen or nitrogen atmosphere. And then, as I mentioned before, the reaction was quite sensitive to the nature of the base. The experiments were done also in the presence of dissolved sodium hydroxide. But it turned out that conversion is very low, as you can see here. So then the conclusion was that sodium hydroxide should be added, at least initially, as a solid. Partial dissolution of sodium hydroxide in the product water is unavoidable, and that's what happened also during the reaction. So what we see here, that under some conditions, which are listed here, with, for instance, this ratio between sodium hydroxide and supported platinum, 1-to-1 ratio at 180 degrees C, it was possible to have rather reasonable conversion with a very high selectivity towards the Gerber product. Here you can see the concentration profiles. You see, I tried to do my best to check the slides, but unfortunately, as you can see here, they are written in Cyrillic, which might be difficult for you to read, but it's basically a molar composition. And here we have time in hours. So I have to apologize for that. But at least one can see here the products. So this is 140, this is 180 degrees C, but hopefully there are some people in the audience. I see Alejandro, who is doing like that. Probably he is able to read in Cyrillic, isn't it? So anyway, selectivity to 2-propyl heptanol was 75–80%, and unfortunately, after some time, the reaction stopped. And then we had to think about what could be the reason for that. And there are 2 explanations, or potential explanations. One would be thermodynamic limitations, and the second, catalyst inactivation. I will return to the topic of thermodynamic limitations after a while. But this is actually quite important to understand, that we have 2 reactions which are a little bit opposite to each other. One is dehydrogenation and another one is hydrogenation. And we all understand that dehydrogenation is favored at higher temperature, while hydrogenation, at least from the thermodynamic viewpoint, is better to run at lower temperatures, even if kinetically it would be favorable to have higher temperatures. So let's start with catalyst inactivation. What could be the reason for that? One option certainly could have been sintering, but that was apparently not the case, since only a minor increase in the size was observed when we compare the fresh and spent catalyst. So a minor increase in size certainly cannot be a reason for deactivation. Could that be changes then in the oxidation state of platinum? No, and as we confirmed by infrared. Could it be because of leaching? The answer is also no, since we have observed only minor leaching of platinum and sodium hydroxide. Coking or strong adsorption? In fact, yes. because blocking of the active sites of platinum by high molecular weight products of side reactions, this is a possibility. And also we have confirmed that there is a possibility of strong absorption of carboxylate-like species on the surface. Coming back to the influence of the support. Here we see the results for 3 catalysts on different supports. One, alumina is more acidic, and as we can see here, selectivity to the desired product, to propyl heptanol, was higher on alumina, which we attributed to the involvement of acid sites of alumina, which is known to be a Lewis acid, in the dehydration steps. So once again, the catalytic system, what we have here is then platinum on a certain support. Alumina turned out to be quite efficient, doped with dry, solid sodium hydroxide. When we introduce sodium hydroxide on platinum on alumina, so the surface area decreased. That was also the same with the pore volume, which also decreased after introduction of sodium hydroxide. In the SPAN catalyst, we had an increase of surface area and the pore volume, which we attributed by partial removal of sodium hydroxide from the pores during the reaction. So adding sodium hydroxide to the catalyst, in fact, resulted in formation of sodium aluminates, which was confirmed by infrared. And sodium aluminate apparently was or is not as efficient as sodium hydroxide for the reaction, not possessing the OH hydroxide group. So our conclusion was that the catalyst inactivation was related to transformations of sodium hydroxide to less active sodium aluminate, and also it's partially related to thermodynamic limitations, as I will explain after a while. Using the Gerber reaction or condensation of another alcohol, C6 of hexanol to 2-butyl octanol through the Gerber reaction. Here, we start with hexanol. The first step will be dehydrogenation to hexanol, then the aldol condensation to this type of compound, 2-butyl to octanol, and then further hydrogenation of that would result in the desired compound, 2-butyl octanol. So let's look at the results were published in Topics in Catalysis 2 years ago. So let's look at the results first. So we here we tested quite a lot of catalysts, as we can see here, based on copper, nickel, and iridium. Even more catalysts were tested, as I will show you after a while. And for the reaction to occur, we had to increase the temperature a little bit compared to C4, C5 alcohols. And the reaction temperature had to be approximately 200 degrees C. Conversion was not that high. And the duration of catalytic experiments was pretty long. So we had all those experiments in the batch mode. And as you can see here, sometimes the conversion was, for instance, 30%, while the reaction time was 95 hours, and we got only hexanol. So once again, our target compound was this one. Yeah. And even with the best catalyst, which was hydrotalcite, we were not able to get the target compound. Then we try identifying that hydrotalcite is a promising material. I mentioned it already before. We started to work more on that, and then we're making hydrotalcite. HT stands here for hydrotalcite, and 400, 500, and 600 refers to the calcination temperature. Then we were also making a different type of catalysts based on hydrotalcites, depositing metals on hydrotalcites, or making the catalyst like simultaneously using the so-called co-precipitation technique. I think I have a type in arrow. on the slide. So co-precipitating the metal together with then precursors for magnesia and alumina. Let's look at the results. Different catalysts were made here. You see the reaction time was pretty long, and then here we see here levels of conversion that are not very high, and then once again our desired product is something like that. So the yields are pretty low, whatever we tried. Once again, we need to have a dehydrogenation reaction requiring a high temperature, and then we need to have a hydrogenation reaction, probably which would run more efficiently at lower temperatures. So low catalytic activity altogether, and the best catalyst, the most effective one, gave just 5% of the desired Gerber product in 24 hours. So then we started to think about thermodynamics and made some thermodynamic calculations. So these calculations were done by our collaborator from the University of Naples from Italy. And then he calculated that the equilibrium composition, he calculated the equilibrium composition dependent on temperature. And it seems that there are very strong thermodynamic limitations. So at least according to the calculations what we done, the maximum yield of the desired product to butyl to octanol would be just 10% or something like that. Actually, water turned out to have a detrimental effect on the reaction rate, and then we started to think, is it possible somehow to improve the reaction rate and even then thermodynamics by removing water? So the best results what we have obtained so far, and at least that's what we published were with co-precipitated nickel and hydrotalcides using calcium oxide as a water scavenger. We had to increase the temperature a little bit, so the Gerber product yield increased to 25%. That is the best result what we were able to obtain so far. The Gerber reaction is interesting in the connection of biorefineries, and here I want to show one example related to the Gerber reaction and making, say, high alcohols from high linear alcohols from such as butanol from ethanol. So there is a company located in the United States, and they have developed a technology, as they say, to build it through biorefineries, starting from ethanol for chemical conversion to butanol. I'm not aware about the industrial implementation of this technology yet, but what I was able to find that they will work with Oak Ridge National Lab to determine the optimal reaction conditions for eventual scaling up of the process. So now I switch from this reaction to something else, which would be then transformations of aldoses to ketoses. This is Lobre de Bruin, Alberta van Eckenstein rearrangement, which requires presence of a base, because when we start with an aldose, which is then an aldo sugar, if we call it like that, and then by abstraction of the proton, and then further rearrangements, we can get a ketose, which is a ketose sugar. So let's check some examples. First of all, this reaction is not new. As an example, I can mention the transformation of glucose to fructose for production of artificial sweeteners. When we start with glucose syrup, the relative sweetness is 40 to 60, but by isomerization of glucose, once again, which is an aldose, it's an aldose sugar, to fructose, which is a ketose sugar, one can increase this relative sweetness substantially. The reaction is done, or this isomerization reaction is conducted in industry on a huge scale using an enzyme which is called glucose isomerase. So some years ago, I have found a number, and that's around 5 million tons per year. So this reaction then in principle would be favorable at high temperature, but the enzymes are not stable, as we all know, at high temperatures. Therefore, the fructose equilibrium concentration is something like that, approximately 50% or so. Certainly a higher temperature would be favorable. Why is this reaction important in the context of biorefineries? A few years ago, colleagues from United Kingdom who are now working in Australia published a review discussing different type of design of catalysts for biorefining, and they were considering this reaction as one of the cornerstones of biorefineries, because then glucose reacts to fructose, and starting from fructose, we can get then HMF, and that will be the so-called platform chemical, given a range of important compounds, including monomers for polymers. Renewable polymers, I would add. So this is then the reaction of glucose to fructose. It requires several steps, as we can see, and we also then we need to have a base catalyst for that. So typically with enzymes, the fructose concentration will be not that high, 40, maybe 50%. Sodium aluminate in water gave 55% of fructose. Then there were also experiments done with hydrotalcides. The yield of fructose was 25%. We didn't want to continue with glucose. Instead, we decided to use two other sugars. One is galactose and another one is arabinose. Arabinose and galactose, they can be obtained from the hemicelluloses arabinogalactan, which is present in such trees as larch species or Larix sibirica. Extraction of hemicelluloses arabinogalactan and further hydrolysis will give, or depolymerization will give us then two sugars, galactose and arabinose. Galactose is a C6 sugar. It's an analog of glucose. The only difference is in the this OH group you see. It looks in another direction, while arabinose is a C5 sugar. Experiments were done using different type of heterogeneous base catalyst, and I mentioned already magnesia as an interesting, potentially interesting catalyst. So when we started with galactose, we had some sort of a transformation of galactose. Tagatose, which is the desired product, was formed, but then we saw a lot of side products. We saw also oligomers. So apparently, in the presence of magnesia, galactose reacted to something else. That's the first thing. And the second, there was a substantial leaching. In fact, the whole the catalyst, the whole amount or charge of catalyst was completely dissolved in the reaction mixture, which is apparently water. In order to say somehow overcome the problems of leaching, we used other type of materials which are known to be more stable, such as magnesium aluminates. So the work was done, or the catalysts were prepared by Maria Kazakova in Novosibirsk. So we had then the materials with different ratio between magnesia and alumina, and with different amounts of weak and medium basic sites. All of the materials were calcined at 680 degrees C. This is a little bit complicated slide, but what I want presenting the concentration curves, what I want to show here are the concentration profiles for different type of materials with different amount of magnesia, 0.9, we see here 0.7, 0.45, 0.2. So apparently, as we can see, the higher is the amount of magnesia, the more active is the catalyst. Unfortunately, the recycling of the catalyst was not very successful. So in the second run, as you can see here, the 0.7 MgO catalyst was less efficient than in the first run. But still, we see some clear trends. Dependence of the rates versus the mole amount of magnesia, or maybe more scientifically correct, would be the rate, or actually more precisely even the rate constant as a function of basicity, which showed almost linear dependence for magnesium aluminates. It's also possible to do this isomerization for sugar mixtures. And we were using glucose, galactose, arabinose, galactose mixtures. And in principle, the catalysts were rather effective. But once again, we certainly have also here thermodynamic limitations. I should now return to leaching. As I mentioned before, when we used magnesia, it dissolved completely. So the magnesium content in the liquid was extremely high. Compared to magnesia, this catalyst had a very low, or I would say almost at the level of detection limit, concentration of magnesium in the liquid phase. So this material demonstrated reasonable stability when it was calcined at 680 degrees C. I think I still have a few minutes, so I want to say a few words about some other reactions of interest in the connection of catalysis by bases. First of all, this conversion of aldoses to ketoses can be done with a little bit more complicated sugars in the alkaline environment. A little bit older work, what we did some years ago, was related to interconversion of lactose to lactulose, and lactose basically can be viewed as the sum of two sugars, galactose and glucose, and then the product in a way can be viewed as a compound comprising two units. One would be galactose and fructose. So in that sense, it's like interconversion of glucose to fructose. Lactulose will then degrade it into galactose and some acid product later on. Another reaction which I want to mention is carboxymethylation of cinnamyl alcohol with dimethyl carbonate. This is a base catalyzed reaction. We start with cinnamyl alcohol, which is the compound resembling the lignin building block. It can be synthesized from cinnamaldehyde. And then when reacting with the green solvent DMC, we can get this cinnamyl methyl carbonate, which is a valuable intermediate in the synthesis of biologically active compound. The work is done in our lab now by Ekaterina Holkina. I can show only the preliminary results for different type of materials. What we tested, MgO was not very efficient. Sodium aluminate was more active than magnesia. Hydrotalcite was rather efficient, even high selectivity and high activity, and the efficiency of hydrotalcite was very close to activity of potassium carbonate, which dissolved not completely, but partially dissolved, maybe by 80% or something like that. So clearly, in the case of potassium carbonate, we have homogeneous catalysis. The selectivity towards the desired product was rather high, approximately 80–90%, independent on whatever it is, homogeneous or heterogeneous catalysis. The last reaction which I want to mention is this one. It's ketonization or ketonic decarboxylation of acids. The review on that reaction related not only to the ketonic decarboxylation, but further high redox oxygenation was published a few years ago together with my colleague Irina in Journal of Energy Chemistry. So once again, this reaction is also catalyzed by bases. We need OH groups present on the surface to run this reaction. I guess it's time for me to conclude. What we have seen in the last 10-15 years is the increasing interest in heterogeneous base catalysis for biorefinery applications. I was also trying to illustrate or demonstrate not only the successes, but also challenges. Challenges related to stability, challenges related to selectivity, those reactions. In some cases, we certainly have problems with thermodynamic limitations, as it is in the case of Yerbe reaction. But I think we need to continue. And I hope the success stories are going to come very soon. And with that, I would like to thank the audience and stop sharing the screen.
Okay, thank you very much, Professor Murzin, for your talk. We have some questions from the audience. One of the questions is that one of the main problems of basic catalysts deals with the easy carbonation, how the carbonation of the basic sites affect their catalytic activity. That's a question from Professor Pecky.
Well, actually, if you can elaborate a little bit more, what do you mean by carbonation? Because there are some reactions where these base catalysts are pretty stable. So if you can probably elaborate more and give some examples, it would be easier for me to answer.
Professor Murzin, that deals with the carbonation, no? Because they absorb CO2 and form carbonates. Calcium, magnesium, and some metal have some, such as lanthanum.
That's completely true. For instance, for some ketonization reaction, it will happen for sure. In some cases, well, it was not done by us, but by some other colleagues. They were using this base catalyst in a fixed bed reactor, and after a while there was no catalyst because the catalyst dissolves completely. It was for in some ketonization reaction, but I would say that it's not always the case. We know in some, for instance, transesterification reaction, do we have CO2 there?
Okay.
I think it depends on the reaction. So when CO2 is not an issue, then it might work. For the second challenge, I would say it's not only carbonation, it's leaching, especially if we deal with aqueous solutions. Because I gave some examples where carbonation was not an issue. For instance, it was this isomerization of aldoses to ketoses. Then there is another problem. The problem will be leaching, which is, yeah, it is an issue.
And that you must change the solvent to avoid that?
Well, it's difficult to dissolve sugars in something else. Because you see, probably Dorothée will also mention, the thing is that we now, and one of the main problems, say, in catalysis related to biorefineries is that we are limited in terms of the solvents. Because if we think about the sugars, we obtain them typically in aqueous media. Because how we extract sugars, like hemicelluloses from biomass? We use aqueous solutions. Then we need to switch to something else. If it's not needed, then it's fine. If we can use organic solvents, then it might be possible to have catalysts which would be stable.
Okay.
Then there was a question. Yeah, I see. There was a question related to enzymatic conversion.
Yeah.
There are two main problems with enzymes in connection to biorefinery applications. There are certainly excellent things related to enzymes, but there are also a few problems. The first one is many of the enzymatic reactions or many of the catalysts are not that active. sometimes the catalysts are not really very efficient in terms of activity, because the nature is actually more patient than human beings. Nature is thinking more about selectivity than activity. So nature had millions, or I don't know, even more years to develop certain reactions. We want to have everything done in 2 hours or in 3 hours. So that will be the first thing. And that is also related to depolymerization of cellulose or hemicellulose using enzymes. The activity is not very high. That's the first thing. The second, in connection to the example which I mentioned, is the thermal stability. The enzymes operate at relatively low temperatures. Certainly there are, when we immobilize enzymes, they can go to 55, 60 degrees C. There are some enzymes which can even tolerate 100, a little bit higher temperatures, but that is the problem. So we are limited with temperature. Therefore, when we move to heterogeneous or homogeneous catalysis and we try to convert sugars, then we are not limited by, say, the set of or by the thermal instability of enzymes, even if when they are immobilized.
Okay, thank you, Professor Murzin. The other question was about the possibility of carry out these reactions in a pilot plant. If you had tried that.
I guess yes. You see, I have a colleague which works on transformations of ethanol to gasoline fuels. So basically, the first reaction, what he's studying, is then condensation of ethanol to butanol. And then there are further transformations, including dehydration reactions and then oligomerization, and then making gasoline. And he runs it now at the pilot scale, and even drives his car using his own gasoline made from ethanol.
Okay, and the strategies for separating or purifying the products after the reaction, how do you see that, if that's a problem, or the strategies for this, if this is such an important subject? I mean,
I think we should discuss it case by case basis. For instance, the Gerber reaction, we start with C5 alcohol, then we get C10. Conversion is reasonable, selectivity is pretty high. So then what we have as a product would be water, our desired product, and then the starting compound with very different boiling points.
Yeah.
So I didn't do it myself, but my gut feeling would be that it is possible, because I mean, it would be possible to have just distillation.
Okay, I have another question about the thermodynamic limitation that you talk about in one of the reactions.
Gerber reaction, yeah, it was a Gerber reaction.
And you try to solve it by taking out the water, yes? And
that was our attempt, and this is something, what probably we should do in this type of transformations, trying to shift equilibrium by removing water. In that particular case, we were using calcium oxide. In some other reactions, we were trying to put a lot of silica.
If it's possible to do the process in steps, different steps, so to work at different conditions, but you talk about
that was finally one of our ideas, because you see, we now need to find a compromise. Certainly, many people are talking about the so-called tandem reactions, that you want to have the tandem reactions because you save on capital costs. You, instead of having two reactors, you have one. Yeah, you have one reactor. You have two or three reactions which are assembled in one reactor to save on capital costs. But then there are some other problems, because then you have thermodynamic limitations. You are not able to have high conversion. Then probably you will lose on the separation section.
Okay. So
not in connection with this example, we have another example, which is also a multi-step reaction with several steps. And finally, we came to a conclusion that it's better to have those steps separately than try to combine them together. Because the idea of saving on capital costs is a good one, but maybe at the end it's not profitable if we consider then also the whole train, including separation.
Okay. Thank you, Professor Murzin, for your talk.
Thank you for the invitation.
Thank you. I pass the word to Professor Pecky. Perhaps to.
Please, thank you, Alejandro. David, you can follow with the presentation, Professor Dorothée.
Okay. Thank you. Okay. Now, we will restart the presentation of Dr. Dorothée Laurenti in the lecture entitled Lignocellulosic Biomass Catalytic Conversion to Chemical for a Safer and Greener Future. Please keep your microphone and camera off, and the question by chat, please. Professor Laurenti. Okay, we are solving some problems. Please be patient. I have some problem with connection again. We are trying to repair this. In the meanwhile, you can go for a cup of coffee, please. Be patient. I am trying to repair this in a couple of minutes. You can use the time to a coffee break.
This Professor Dorothée is there. David, you can unmute her, please.
Okay, can you hear me? Yeah,
yes.
My microphone was cut. I'm really sorry. I'm on holiday actually this week, and I am not at home and I am not in the lab, and my connection is very bad. I'm really sorry, and I apologize for all of this. And I'm trying to continue my presentation. I like to share my screen. Okay. Could you see my screen?
Yes. We can see your screen.
Good. Just 1 minute. Okay, okay. So I will continue. Is it okay for you, or do you want me to come back to the beginning? It was just the introduction, so maybe I can continue. Are you okay?
It's okay, Professor.
Okay, thank you very much. So I'm continuing with the different listing of catalysts for biomass conversion, heterogeneous catalysts. Effectively, catalysts are highly needed to improve the yields and the quality, especially of the bio-oils, and to decrease the char and solid formation during biomass conversion. So in general, a long list of catalysts can be used, like metals, metal sulfide, carbides, nitride, phosphide, oxide, or zeolites, or over-ordered porous solids. And as Professor Murzin told us, it is very interesting to add a bifunctionality with addition of acid sites or basic sites. In general, the metals used are noble metal. They are very active in biomass conversion, but of course they are expensive. So there are a lot of attempts to lower the cost of the catalyst and using nickel or iron metals. And for metal sulfide, it is often molybdenum or tungsten, which are the metal sulfide used. And then we have to deal with the deactivation of those catalysts because of the components in the biomass. You can have some poisoning, but also some degradation and leaching due to the operating condition in polar media. And also, we have to recycle the catalyst. It's very important for us. And this can be done by cleaning, reduction, or oxidation. So we have to face all these problems. Then this is a chart which
Okay, I apologize for the technical problems, but we are starting the presentation in a while. You have more time to prepare your coffee, maybe take some cookies. We will start in a while, please be patient. Okay, you know, the presentation will be, the record of the presentation will be available after that in the website of the Millennium Nucleus. And at the same time, this presentation is transmitted by YouTube in streaming. You can look for this presentation in YouTube after that if you want. And we have another question in the chat. Yes, we will have more webinar in the future, maybe in the end of the year, and the next year we will have more events. And please, you are kindly invited to visit our webpage, where you can see a lot of activities we are developed, especially for for the community, for the school. We have a lot of activities you can see. And this webinar will be continuing in maybe at the end of the year or the next year.
Hello again.
Hello, Professor.
I'm very sorry. Do you want to start again, or do you want to end? I don't know what to do.
No, don't worry. We are welcome. Whatever will be more easy for you, you can continue.
Okay. I try to continue, and if I am disconnected again, what I propose is to register my presentation and to send to all the participants. And
thank you very
apologize again.
Oh, thank you very much. Thank you very much for your kindness to
so I'm trying to continue, and if I am disconnected, I will share with you the presentation.
Thank you. Professor, maybe if you turn off your camera, it could be increased the
maybe
internet rate.
Yeah, maybe, but I think it's another problem. My box is switching off every 5 minutes, so it was working when Dmitry Murzin was talking. I could listen, but now I don't know. I'm trying to start again. But I think somebody has deactivated my sharing of the screen. The sharing of the screen, please. I cannot do it.
Okay.
Somebody has deactivated it.
Okay, we will work on this.
Yeah.
Now you can try now.
No, yes, it works.
Oh, thank you.
Okay. So sorry again, I continue. So I was talking about the different process to liquefy lignocellulosic biomass, including pyrolysis, solvolysis, hydrolysis to get biooils or sugars and lignin. And then conversion of this biooil or these sugars and lignin with or without catalyst to get biofuels and biochemicals. So you can see that catalyst can be here for most of the processes. And I'm going to talk about the three processes in red just now. So first, I like to talk about HDO of pyrolytic biooils, HDO for hydrodeoxygenation. And usually these studies are carried out with guaiacol as a model molecule because it is one of the representative molecule in biooils, and it is quite refractory to hydrotreating. And we used in this work metal sulfide catalyst to study the support effects. Here you've got the general scheme of transformation of guaiacol to the various products with this kind of catalyst. And in fact, when we compared various support for COMOS catalyst, we observed a very high intrinsic HDO rate for the catalyst supported on zirconia compared to titania or alumina. And in fact, it is because with this catalyst, COMOS supported on zirconia, you've got direct deoxygenation reactions. and you go directly from guaiacol to phenol and then to benzene. So it's very, very efficient, but it is realized in gas phase. So you've got only guaiacol in gas phase in contact with the solid catalyst. Then we tried the same catalyst, but in liquid phase. We performed the HDO of guaiacol in liquid phase, in dodecane, for instance, and we observed that in liquid phase, COMOS supported on zirconia, alumina, or titania had exactly the same catalytic activity or very close. So we have to be careful because sometimes analogy between gas phase and liquid phase can be very limited because the interaction of the solvents, there are some competition, there are solvating spaces, the mass transport limitations, and structural changes in the catalyst. And also you can have, in the case of real feed of biomass conversion, interaction with the other components, including water, and it's not trivial. So we suggest that a mixture of molecules could be more representative for this kind of reaction than model molecule. We performed bio-oil hydroconversion or stabilization in the collaborative work with IFPEN. It was Matthew Zagak, PhD. So here, this scheme is representing the fast pyrolysis of bio-oil, which leads to bio-oil with a lot of oxygen. It's unstable, acidic, and immiscible with hydrocarbons. So you must perform a first stabilization step at low to moderate temperature and pressure. And then you will perform a real hydroconversion step at higher temperature to fully deoxygenize the oil, and you get aqueous phase. And after several refining, you will get a liquid which can be dropped as a biofuel. So we studied the nickel molybdenum supported on alumina catalyst in reduced form for this first step of stabilization to improve the further hydrotreatment. So in order to choose a representative model molecule for this mixture, we considered the characterization by GC-GC of a pyrolysis bio-oil. So you can see here the various family which are typically found in those bio-oil like furan, guaiacol, sugars as levoglucosan, phenol, furanone, acetic acid. And then we have chosen glucose, furfural, acetic acid, and guaiacol as the 4 model molecule, and we also used water to make some blended mixtures. Here, you can see the reaction scheme we have drawn after glucose as a lone molecule, model molecule in hydroconversion on the reduced NEMO catalyst supported on alumina and under hydrogen pressure. You can see that
I'm sorry, we have some problems again, but don't worry, the full presentation will be available in the web page. Okay, please, we apologize for this problem, technical problem. With internet, you know, in this time, all of us, we have some problems some days with the internet, especially when you the lecture. The full presentation will be available in our webpage in order to see, and you can do the question by email or to us or directly to Professor Laurenti. Now Professor Pecchi will be the last speaker of the day, the last activity. Professor Pecchi.
Thank you, David. So finally, we want to thank in a very special way our speakers, Professor Dorothée, Professor Dmitry, for their interesting and update conferences related to biomass recovery. We also feel sorry about the problems of Dorothée, and we hope that we can have another opportunity to listen to her conference. Many thanks also to all of you present in this first Millennium Nucleus webinar. I have to say that we became more than 1,030 connected through Zoom platform and Google, YouTube. So thank you very much. Take good care of yourself, and please turn on your cameras and smile to take a picture. Okay, there's a very beautiful view. Professor Dmitry, thank you for your participation, and all of you, we hope to see you soon. Bye, and thank you very much.